Hold on. Okay, so we're going to talk about today's, right now, section 7.2, direction fields and Euler's method. So you've learned, you've been introduced to differential equations. You know that a differential equation is an equation that has derivatives in it. And you know how to check to see if a solution, you know how to check to see if some expression is a solution to the differential equation. And, our goal, of course, eventually is to try to solve the differential equations. But it's a fact that there are many differential equations that cannot be solved. You cannot formally find a solution to some differential equations. But just because you can't find a solution to some differential equations doesn't mean you can't understand what solutions look like. And that's what section 7.2 is about. In this section, you're going to qualitatively, you're going to learn that you can actually get a visual idea of what solutions look like, even though you don't have a formula for the solution. And this relates to something called direction fields. So you see here, this is from the ebook, section 7.2, and we're dealing with the differential equation y prime equals x plus y. Now that differential equation, you're not going to learn how to solve that in this course. Okay, that kind of differential equation. But we do know that, what do we know about our solution y? Well, we know what its derivative is, because we're told that y prime equals x plus y. So that means that if you give me a coordinate, any coordinate xy, I can find out the derivative at that coordinate, at that point, which is the same as finding the slope of a tangent line to the solution at that point. So once again, I can find, being that I know what the derivative is of my solution, any point on the solution, I can find the value of its derivative for whatever coordinate xy you have, and then that value of the derivative represents the slope of the tangent line of the solution at that point. So what they have here is they have y prime equals x plus y, and they're looking in this figure at a solution of y prime equals x plus y. They're claiming that this is a solution, this curve here. Now, you'll notice that the tangent line the slope is negative in this quadrant. Well, I got to be careful here. We're in the second quadrant, right at this point. The slope of the tangent line is negative. And in the first quadrant, the slope of the tangent line is positive. So at the coordinate x1, y1, the slope is x1 plus y1 because y prime equals x plus y. And then at the second point, x2, y2, the slope is going to be x2 plus y2. Could anybody tell me why in the first quadrant that, they haven't even specified a point. The point x2, y2 is just in the first quadrant, and they're drawing a tangent line with a positive slope. Why would the slope be positive? Why would the slope be positive there? Why would that point, the tangent line at that point, have a positive slope? Why must the slope be positive? Remember, y prime equals x plus y. And so here, the slope is x2 plus y2. Tangent line has a positive slope. Who thinks maybe they can tell me why that is? Very good, Marvelous. Very good, Robin. That's exactly right. In the first quadrant, all the xy coordinates, the x coordinates positive, the y coordinates positive. So no matter what x2 and y2 are, if you add them, you're going to get a positive value, and so the slope is going to be positive. Now in quadrant 2, they've positioned the coordinate x1, y1 so that the tangent line to the solution at this point has a negative slope. And that would make sense because if you look at that point, whatever the coordinate is, the x1 value is negative, the y1 value is positive, but x1 is more negative than y1 is positive, and so the slope there would be negative. Okay, are there any questions on that concept? All right, well, now in figure 2, they actually pick a point, 0, 1, and compute the slope, 0 plus 1 equals 1, because y prime equals x plus y, and they draw a little tangent line there with a slope of 1. Okay, so, you know, we can do this process. We can pick, you know, a bunch of points, throughout. That's not a point there. But you can pick a bunch of points throughout the xy plane, and you know, every point has a coordinate, and you can compute the slope of the tangent line to the solution at that point, because that's what y prime is. It's the derivative of the solution, right? And if you were to do this, you would get something called a direction field. Sometimes it's called a slope field, but we're going to call it a direction field. And the direction field is here. Here's your direction field. And what they've done in figure 3, so I mean, how did they get all these tangent lines? Again, they picked a bunch of coordinates in all the quadrants, computed the derivative, and then that was the slope of the tangent line of the solution, and they drew the tangent lines. And the thing is, the tangent lines guide you as to what the solution has to look like, because the solution has to obey those tangents. So like if you were interested in, you know, y prime equals x plus y, the solution for y prime equals x plus y, and you have the initial condition 0, 1 here, you know, that means y of 0 equals 1, then the solution for that initial value problem would look like this parabola. And it may not be actually formally a parabola, but it looks like this curve. All right. If you had a solution, say you had a solution, well, are there any questions on that so far? Are we okay with that? Okay. So one thing that's interesting here, let me get my shape thing. I want a line here. I'm looking at this direction field, and it looks to me that if I want the solution that passes through the origin, that solution, I want to be careful here. One moment. One moment. Yeah, so you have, let me put this here in red. I mean, you have, looks to me like, you know, the solutions, they're, well, hold on, we don't want the figure anymore. You know, I don't want text either. Solutions are curvy here, but they start to kind of straighten out. See that? They start to, so this isn't perfect, but they're kind of straight, leveling, they're straightening out. They're straightening out. And this solution here that passes through the origin is going to be a straight line. Why is that? Who might be able to tell me why, you know, the solution passing through the origin, 0, 0, is going to look like a straight line? It's not a curve. It's, you know, it's not like these, you know, curves here. Does anybody know? So y prime equals x plus y. Could you tell me what the equation is of this line that I drew here through the origin? Could you make a guess? That's right, Robin. Y equals negative x. Excellent. Well, if y equals negative x, this means that, hold on here. Just give me one moment here. This line, all right. So the line, I guess what I'm asking is, I want to be a little bit careful here. I said something incorrect, not right. This blue line I drew is not a solution to the differential equation passing. It's not a solution to the differential equation where the solution passes through the origin. But I'm noting that all the tangent lines along the line y equals negative x, all those tangent lines appear to have what kind of slope? All the tangent lines along in your direction field, all those tangent lines along the line y equals negative x, what do the slopes appear to be? The slopes are flat slopes, right? Flat slopes. All these slopes are flat along the line y equals negative x. All these I should say all the tangent lines are flat along the line y equals negative x. So if that's the case, what does a flat tangent line, what's the slope of a flat tangent line? That's right, Sumaya. Very good. 0. That's right. And that would make sense because along the line y equals negative x, if y equals negative x, then y prime is going to equal x plus negative x, right? And that equals 0. So you can, so it makes sense that the tangent lines would have, the tangent lines would be flat along the line, along that line, y equals negative x. All right, are there any questions on that? So I'm not saying y equals negative x is the solution, but what I'm saying is along the line y equals negative x in that xy plane, all the tangent lines in the direction field are flat. And the reason is because when y equals negative x, all the coordinates that are on that line, y prime would have to equal 0. Because if you substitute in y equals negative x for y, you'll get y prime equals 0. Are there any questions on that? All right, and the reason that I'm showing you this is at this stage, you know, we want you to be able to match up direction fields, you know, with the differential equations that are given. When you get into the coarse differential equations, you'll need to graph direction fields, and they'll be more complex, and you'll be using probably MATLAB to graph those direction fields. MATLAB is a programming language that's used in engineering and science. But at this stage, we just want you to be able to, hey, you know, given a direction field, can you match it with a differential equation? And what I did was I made use of the fact that there was an interesting pattern, you know, along here of flat slopes, you know, and I show you why that's true. So let's move on here. Let's move on. So they give an example here using a direction field to sketch a solution curve. This is in your ebook, and they say sketch the direction field for the differential equation y prime equals x squared plus y squared equals -1. Okay. So what they do is they pick a lot of xy coordinates and compute the derivative at every point. They pick enough so that they're able to get enough slopes so they can draw the direction field. Okay, so like for instance, at -2, 0, right here, that point, when x is -2 and y is 0, y prime would be -2 squared plus 0 squared minus 1, and that's 3. And you notice the tangent line, right here is looks like a slope of 3. On the other hand, at the origin, 0, 0, if you compute y prime, you get negative 1. So at the origin, okay, you get a negative slope there. Okay, so you know, they pick enough points so that you could get an idea of what the direction field looks like. But oftentimes you don't have to pick a lot of XY coordinates in order to get the direction field, particularly if it's like if it's a matching problem. I'm just trying to think here if there's any. Let's see, just give me a moment here. Yeah, okay, so we won't need to talk more on this. But then on, well, one more thing. They say use part A to sketch a solution curve that passes through the origin. So in this example, what they do is here's the origin, and they draw a solution curve that obeys the tangent lines. The solution curve must follow you know, its tangents. Tangents to the solution are drawn in the direction field, and your solution curve has to obey those tangent lines. That's how you draw a solution curve. And in your web-assigned homework for section 7.2, a lot of the problems are multiple choice, where, you know, if you know, maybe have 4 pictures, right? And each picture has a different solution curve. Well, if there are 4 choices, multiple choice problem, how many tries do you have to get the question right? I think you all know this, but well, you know, I think you all know it's 2 choices, right? Two tries, okay? So you just want to be a little careful working the exercises out. And so to you know, these direction fields, what I have here is a little exercise that I want you to do here. All right. This is actually one of the examples, not an example, an exercise in the book, in the textbook. And what you have here is you want to match the differential equation with its direction field. And you have 4 direction fields, A, B, C, and D here. And, well, I'm sorry, you have 4 differential equations, A, B, C, and D. And then you have 4 different direction fields. And you have to match the direction field with which differential equation it goes with. So what I'd like you to do is think about, you know, think about this, how to go, like work on this. So like just sort of kind of get you started, here. The first differential equation is y prime equals 2 minus y. Now I don't want to plot, you know, 10 different coordinates and compute the slope for each of those coordinates and draw 10 tangent lines with the corresponding slopes. I don't want to do that if I don't have to. So what I want to do is I want to pick out some important feature of that differential equation, y prime equals 2 minus y. So what is an important feature, you know, that would be helpful to look at for that differential equation? Who thinks they can chat it out? What would be an important feature? Is there any interesting value, for instance, of y that we might want to look at? That's right, John, when y equals 2. Well, let me ask you, for the first differential equation, when y equals 2, what does y prime equal? What does the derivative equal? What does the slope equal when y equals 2? That's right, John, 0. That's right, Tyreek. Good. So that means then that along the horizontal line, y equals 2, for this differential equation, okay, for y prime equals 2 minus y, the direction field along the line y equals 2, along that horizontal line, the slopes have to be flat, because along y equals 2, along that horizontal line, y prime equals 0. So now I go and look at the 4 direction fields, and which candidates would be ones where along the horizontal line y equals 2, y prime along the horizontal line y equals 2, you have flat slopes in the direction field. What candidates might we be able to might work? 3, John's right on that. And that's right, Robin. Robin's right on that. So you have choice 1 and 3. But now you have to decide between 1 and 3, which is right. And it helps now to, look at the other derivatives. And, notice B is y prime equals x minus 2y. Right? So, now they throw in an x there as a factor. So this is the kind of thinking that I want you to do for this example, this little exercise. So take a moment, take about 5 minutes here, and see if you can match the direction field with the differential equation. Okay, take a few moments to work it out. This is something that's really nice, if we were like meeting on campus as a group, students could sort of naturally help each other. But you can certainly chat out information to everybody to get input. I mean, so take about 5 minutes and let's see if you can get the right answers here. This is a really nice class activity, but we're going to have to do it remotely. So, I guess as students, you can chat with everybody in the class, or you can maybe pick certain people to chat with in the class. So, like sometimes this is a nice exercise to do in groups. So like maybe if you know a couple people in class, you could share your answers with them and get their input, sort of naturally break up in groups. That's up to you. Okay, so giving you a little time here.
Yeah, I didn't do that.
Okay, a few more minutes here. Okay, so all right, let's start with A here. Y prime equals 2 minus y. So for A, we said it could either be choice 1 or choice 3. Which choice would A go with? Roman numeral 1 or Roman numeral 3? John thinks 3. All right. Robin thinks 3. Okay, good, good. Well, so it helps to, let's say that okay, let's put 3 for A. Then for B, the choice would have to be, what would then the choice naturally have to be for B? That's correct. That's right, John. Choice would have to be 1 for B. Because you see, B has the extra factor of x there. So you notice in 1, you have flat slopes along the line y equals 2, but you also have flat slopes along the y-axis. You don't see flat slopes along the y-axis in choice 3, but you do see flat slopes along the y-axis in 1. Well, what is the equation of the y-axis? What is the equation of the y-axis? Who can chat it out? The y-axis is a vertical axis. Okay, so you've dealt with vertical lines before with your rotating curves and finding volumes. So what I'm asking is, this y-axis has an equation x equals what? Don't be shy. That's good. Thank you, John. X equals 0 is the y-axis. So only in choice 1 is, so if we substitute x equals 0 for our differential equation in B, we're going to get y prime equals 0 there as well. So for differential equation B, the derivative will be equal 0 when either x is 0 or y equals 2. So y equals 2 is this horizontal line, okay, where the slopes, hold on here, where the slopes are flat. And x equals 0 is this vertical line here. Slopes are flat there. Even though in choice 3 the slopes are flat along y equals 2, the slopes are not flat along that vertical line x equals 0. So far we're doing well. Now, let's look at choice C. D is a little bit complicated. Well, it's not that bad, but I think C is a little bit easier. What do we want to do with choice C to help us evaluate that? What do we want to set y prime equal to? What's very helpful to set the derivative equal to? We did it in A and B. We were looking for when the derivative was equal to 0, right? Yes, John and I said it at the same time. So here, y prime will equal 0 when x plus y minus 1 equals 0. Okay? That's when y prime equals 0. Or when y equals 1 minus x. So what I'm saying is, y prime equals 0. And I'm sorry, I'm writing it writing it the best I can. I know it's not great, but you know, see, that's one reason too I put it in my closed captions too, because sometimes, you know, I need to maybe in the future get a drawing pad, but you know, the college I mean, it would be nice, of course, if the college would provide that to us, and hope maybe they will this coming fall. But perhaps I'll get one then. If they don't, you know, sometimes you gotta spend a little money. You know, I don't think they're that expensive. But at any rate, all right. So y prime for this this third differential equation, y prime equals 0 when y equals 1 minus x. 1 minus x is a line whose y-intercept is 1 and has a negative slope. So you see, if I look at, let me go to blue here. Shape line. If I look right here at equation 4, the slopes are all flat. What I'm doing is I'm drawing a line passing through the 0.01. That's your y-intercept. You know, it's right there, right? So hold on here. It's right here. That line, along the line y equals 1, x, 1 minus x, the slopes are flat. I don't see that behavior in choice 2. So therefore, the answer here for C is going to be choice 4. And then by process of elimination, D is going to be choice 2. Okay? Are there any questions on that? All right. How many of you found this little example, this little exercise, fun? Kind of cool. Okay. Thank you, John. Thank you, Tyreek. Thank you, Sachi. Excellent. Thank you, Gabriel. Excellent. And, you know, see, there's value. I mean, I'm glad you're in class today. We only have, I mean, well, we have 14 students, but normally we have more. So some students are not attending class like they should. But, you know, you're attending class, and my goal is to make it very worth your while. So you're learning a lot of good things here. Sometimes when students, you know, yes, thank you, Raymond. Excellent, excellent. And, you know, so good. All right, so let's proceed on here. So now, so we have a way, yes, thank you, Raymond. So we have a way now to quantitatively find, if we can graph the direction field, like I'm just blowing up a little picture here of a direction field that went with example, let me see here, example 1. Oh wait, hold on. No, I got to be careful here. This figure 8 is just a direction field corresponding to some differential equation. And if we know the direction field, we can graph all the solutions that are possible. Okay, I mean, I mean, we can see a family of solutions here in this figure 8. There's a family of solutions, and of course, what determines which solution's which is the initial value. So, like this solution here has a different initial value than this solution does down here. Okay, but you can see a family of solutions, and it's nice to have a qualitative, a visual or qualitative feel for what the solutions are. But still, without a formula, we can't make approximations. You know, we can't get values. I mean, we can look at the picture and approximate, but that oftentimes isn't accurate. There's a saying in statistics that your eyes will fool you every time. So the point is, we want to try to be accurate. So we need, when we have differential equations that we can't get solutions for formally, we need to have a way to, and you know, we use formal formulas, formal solutions, so that, you know, if x equals this value, y equals that value, we can compute y values for the solution given x values. But if we can't get a formula, we have to use an approximation technique to get values. And to do this, we use an approach called Euler's method. Okay, and Euler's method is in your section 7.2 in the textbook there. And actually, what I had to do, if you look in your ebook in section 7.2, they have a, let me see here, one moment. They have interesting information regarding Euler, the gentleman who came up with this approach. Let me just see here. It's probably worth me bringing it up. Let me go into the ebook, and you can go in as well. One moment. All right, share the application, Chrome. Okay, so I'm in the ebook here, and I'm going to this chapter 7. And let me get the menu open there. And we'll go right to Euler's method. And this allows us to approximate solutions to differential equations. But there's information on Euler. Let's see, maybe it's not, oh yeah, so below the Euler's method, there's a footnote on Euler. Who's heard of Leonhard Euler before? Have any of you heard of this mathematician? He was the leading mathematician of the mid-18th century and the most prolific mathematician of all time. You know, his calculations and writings, there are many of them, they're volumes. Well, it says here there's 100 large volumes of his work. Imagine that. You know, I mean, even people that write English books, write, you know, books for entertainment, a lot of them don't have 100 volumes. But this mathematician did a lot of work. And he came up with this method. And by the way, his writings weren't diminished by the fact that he raised 13 children, or, you know, and also was blind for the last 17 years of his life. Now, I'm going to comment here. I'm sure he had help raising those 13 children, okay? You know. But all right, so let me go back here to the example. But how many think that's kind of interesting, this information about Euler? How many think that's pretty cool? Excellent, excellent. John likes it. And there's you know, there were some female mathematicians too. Thank you, Gabriel. There were some female mathematicians also, like everybody's heard of Sonia Kovalevsky. You know, there are more female mathematicians now, but back then you know, they had some. Sonia Kovalevsky was famous. How many have heard of Sonia Kovalevsky, the famous mathematician? Has anybody here heard her name before? Well, you have now. You have now. All right. So let me go here and stop the sharing on this, and let me go back to the example. Okay, so Euler's method. So we're looking at that differential equation again, y prime equals x plus y. Okay, that's the one that they had before when they were talking about direction fields. And we have this initial condition y of 0 equals 1. So, all right, a first approximation, if you're at, and there's figures here, 2 figures below, figure 13 and 14. If you're at, you know, this initial point, 0, 1, okay, I'm trying to just put it, let me see here, can I get that drawn right? Yeah, that point there, 0, 1, we know, since we know a point, 0, 1, and since we know the slope of the solution at that point, y prime equals x plus y, so the slope of the solution is 1, Well, we have a point and a slope. We can get a line. So once again, for the coordinate here, let me erase that. This is why I need the space here. For the coordinate, my gosh, I can't draw this right. Hold on. It's just hard doing it with the mouse. Let me try again here. So the coordinate 0, 1, y prime is going to equal 0. This is a comma here. 0 plus 1, which equals 1. And we know that y minus y naught, which would mean y minus 1, at the point 0, 1, the equation of the line that passes through the point 0, 1 and has a slope of 1. Okay, if we use the point slope formula, that's y minus y naught equals m times x minus 1. So y minus 1 equals the slope 1 times x minus 0. And so y will equal x plus 1. Okay, that's how they get this right here. All right, are there any questions on that? All right, well, what they've done is at 0, in figure 13, at 0, 1, they've drawn, and again, it's not perfectly to scale, but they've drawn a line segment starting at 0, 1, and the line segment, it has equation y equals x plus 1. Now, the line segment, they draw the line out to 0.5. To x equals 0.5, because so what they're showing here, is they're showing the actual solution here to this differential equation, but we don't know what the formula is for that actual solution, but we know it like that. So what if we wanted to now hold on here. Just making sure we're comfortable here. What if we wanted to approximate what the solution's value is when x is 0.5? Okay. So in other words, I'd like to know here. I'd like to know what y of 0.5 equals, what does it equal? Am I going to know exactly? No, I'm not going to know exactly because I don't have the formula for the solution. But I do know I can use the Euler's method to help me. So this line segment here, this line segment that we drew, it's based on the line y equals x plus 1. The line segment approximates the solution in red. It approximates it. And just like at the point 0, 1, we used the Euler's method to give us a line segment that approximates the solution. When x equals 0.5, we can also use the Euler's method to give us another line segment maybe I'll put this in orange, to give us another line segment that approximates this portion of the solution from 0.5 to 1. So how are we going to do that? Well, all right, how are we going to do that? So do we know the slope when x equals 0.5? Of course, we need an x and a y. When x equals 0.5, y equals 1.5, because if you put x equals 0.5 in for that line, y equals x plus 1, you're going to get 1.5. So you have the coordinate here. You have the coordinates 0.5 and 1.5. Those are the coordinates for this point right here. And you know what y prime is. Y prime at that point, okay, the derivative at that point is going to equal 0.5, 0.5 plus 1.5, okay, and that equals 2. So again, you can get the equation of a line that starts off at 0.5 and 1.5. The equation of the line would be y minus 1.5 equals 2 times x minus 0.5. And if you work that out, okay, if you work that out, you're going to get y equals 2x plus 0.5. And I'm doing it the best I can. Again, the closed captions will assist in this, but you know, I mean, it's the writing is you know, it's not like perfect, but you know, I think it's clear enough so that you can see what I'm doing. Okay, so again, now we have another line segment, y equals 2x plus 0.5, and that's drawn in yellow here. And so this portion of the solution from 0.5 to 1, we can approximate with this line segment. This is called stepping out along the direction field. And you know, what happens to these linear approximations as we move away from our original starting point, 0, 1? Do the approximations, the linear approximations, line segment approximations to the solution, do they get better or do they get worse as we move away from our starting point, 0, 1? Do they appear to be getting better or worse? In figure 13 there. Who can shout out an answer for us? That's right, Robin. Excellent. They're getting worse. Okay, they're getting worse. But look here, in figure 14, they approximated the solution curve from 0 to 1 using 4 line segments. So in figure 13, they approximated the solution using a step size of 0.5 So 2 line segments took you from 0 to 1. But if you use smaller step size of 0.25, you need 4 line segments to approximate the solution from x equals 0 to 1, you know. And does the approximate solution is it better when the step size is smaller, of 0.25? Is it better? Or is it worse? Definitely better. Yes, that's right. Definitely better. And so you see, that's the beauty of the Euler's method. Even though you don't know the actual solution, a formula for the actual solution, if you have a small enough step size, you can get an excellent approximation. And with computing power these days, you know, like in differential equations, you'll learn how to program Euler's method in MATLAB, probably MATLAB, and you'll be able to get excellent approximations to the actual solution. Okay. Of course, for your homework, the problems, the Euler's method problems, you're going to be working them out by hand, and the amount of work is reasonable that I'm giving you. But are there any questions so far on this process of Euler's method? Okay, well, let's formalize this method a little bit. Okay, let's formalize the Euler's method. So, and this is in your ebook, and you know, I try to make the you know, when I do the scans, sometimes the pages aren't perfectly straight, but this is okay. What we've done is, what I've done is I've shown you 2 steps of Euler's method. 2 steps. And we can continue this, like for the, you know, what we did the 2 steps of Euler's method with the step size of 0.5. So this is the iterative approach that what we've done. Approximate values for the solution of the initial value problem, and there's a typo here, it should be y prime equals some function of x and y. That's what you see on the right-hand side of the differential equation. Approximate values for the solution of the initial value problem, y prime equals some function of x and y, where the value of y at x naught equals y naught, with step size h, is given by this iterative formula. Now, they're saying that the approximate value, the nth approximate value, is y sub n is dependent on the value that the approximate value that came before it. That's y sub n minus 1 plus h times the derivative of the based on the coordinate that was used before. So a new value, a new approximation value, is based off of the line that you had for the based on the previous approximate value. So, like for instance, if we work out Euler's method with a step size of 0.1 to construct a table of approximate values for this differential equation, they show you the first 3 steps. Okay, the first 3 steps. Okay, so the y1 equals y sub 0 plus h times the derivative evaluated at x sub 0, y sub 0. Well, y sub 0, you know, you're told that, you know, x sub 0 is 0. That's here. and y sub 0 is 1. So y sub 0 is 1, h is 0.1, and when x sub 0 is 0 and y sub 0 is 1, the derivative is 0 plus 1, and you get 1.1. So that's your first approximation. Your second approximation, y sub 2, would be y sub 1 plus h times the derivative evaluated at x1, y1. Well, y1 now, y1 is now this value, 1.1, so that goes here. And then the derivative is x1 plus y1. So that's 0.1 plus 1.1. The 1.1, of course, is the y1. x1 is 0.1 because you're moving out a 0.1 distance from your initial x value of 0. And so you get 1.22. Okay, finally for y sub 3, and you don't need to really copy this in your notes unless you want to. I mean, I'll kind of go a little bit slow here. How many are actually copying this example 3 down in their notes? Is anybody actually doing that? And that's fine if you are. Okay, excellent, excellent. All right, so let me just slow down a little bit and are there any questions on the first two? Thank you, John. Thank you, Robin. Any questions on the first 2 iterations? All right. So the third iteration, y sub 3, is again computed using the previous information. So that would be the previous approximation, y sub 2, and then the derivative evaluated at the x2, y2 point. Well, x2 is going to be 0.2 because you're moving out 2 steps. So hold on here. Let me get the shape here, the line. Okay, so 0. Now wait, hold on. Now I gotta get rid of the shape. Go back to this. Okay, so you have 0. You have 0.1. You have 0.2. And so forth. All the way. Well, they're approximating values, and y of 0.3 is going to equal one moment here. Let me just yeah, y of 0.3 is going to equal 1.362. You can keep going with this approach. You can keep going with it, and they have here a table where they have done 10 iterations. So if you're using a step size, of 0.1, and you're interested in what y of 1 is equal to, you don't know the solution, the formula for the solution for y, but you want to know when x equals 1, what does y approximately equal? I can write that a little better. Let me just write that a little bit better. Okay. Well, if you start at 0 and you have a step size of 0.1, how many steps do you need to go till you get to 1? How many steps would that take? Who can shout out the answer? That's right, Robin. Very good. 10 steps. 10 steps. So this is how you use Euler's method. This is how it works. Okay. Are there any questions at all on this? And remember, just so you know, the step size, you can control how large h is. If h were equal to like 1/100th, well, you would need 100 steps to get to approximate y1, and that would take a long time to do by hand. But with computing power these days, that would not take, or that wouldn't take any time at all. But back then, these mathematicians, they were working with astronomy and the stars, and they needed to compute values. They needed to compute things, and so a lot of these computations they would work out by hand. They might have an abacus or something to help them, but a lot of computation back then. And now this computation, we've used computers to help us. But of course, for your WebAssign homework, I want you to work the problems out by hand. And your next exam, I would expect you to work out everything by hand, just like they're doing in this example 3, so that you can show me you understand the process. Okay, and again, the number of iterations should be reasonable, so that it won't take too long. Okay. All right. So now, what I want to do, I do want to move into section 7.3. I want to discuss some examples there, but I'm going to stop and give you 20 minutes of class time to work on section 7.2. Okay. So just give me a moment here. Let me go into 7.2 here and make that available for you. That assignment's the one that's due Saturday. Okay, let me take off the restrictions. 7.2, you have to be a little bit careful with 7.2 because a lot of the problems are multiple choice, and so you just have to, not answer too quickly. The direction field kind of problems. So let me take off the restrictions here. Okay, are there any questions, by the way, on this example? Are we good? All right, I'll stop the recording.